Okay, so I have some bullet points. I actually have 3 different slides worth of bullet points because we originally had 3 different areas of discussion. I'm just going to briefly read through them and then kind of open it to the room. We can discuss whatever we want. So for the morning discussion, some of the things we had originally thought about talking about is, does the existence of LLMs change how we should be preparing physics majors, both in research and in terms of jobs in the real world? Which is relate to the point of how will LLMs impact both the academic and non-academic job markets, because they are potentially replacing the need for some skill sets and creating needs for new ones. Can MIT be doing anything to shape how LLMs influence global society? I think Max hinted at some potential dangers there. And here's kind of an interesting question. Are there any areas that are just not going to be affected by LLMs, where they're not going to be useful? In the research area, how will the LLMs change the roles of graduate students, postdocs, and faculty in research? You just saw some of what they can do. How might that change your daily life? Will LLMs transform analytic work areas such as theoretical physics? If they can already solve 801 problems, will GPT-5 start doing quantum field theory at a level beyond us at some point? Are they capable of being creative? Can they discover physical laws? And something that Jan brought up that I think we should think about, what happens if AI far surpass what humans are capable of understanding and they just start explaining new physical laws to us and we're not even comprehending them anymore? And then finally, on the teaching and administration side, based on what you've seen, how might you run a classroom different in the era of the existence of LLMs? Should we be worried about students trying to use them to do their problem sets and actually hindering their own learning? Should we start thinking about teaching students how to effectively use LLMs to solve problems if we think these are going to become a thing that's important in everyone's daily life? Could the LLMs become proficient teachers? Could that even replace sort of the role of faculty in the classroom to some degree if they get very, very good at explaining concepts? So those are just some bullet points to get started. I know there was a lot there. I'll go back to the first slide. But I just kind of want to open it up to the room. So if anyone wants to come up to the mics, or if anyone up here wants to grab a mic and talk, this is the time.
Yeah, so I had a question for everybody, but probably mostly Kevin. So since you were able to show that it's actually able to solve a lot of 801 problems, do you think it's still valuable to be teaching kids and spending all of this time teaching kids 801 when they can just look it up?
Does someone want to say something there? Or someone in the audience? It's a good question. I mean, the example I've been thinking about in that context is when the calculator was invented, did we stop teaching people how to do multiplication or division? We didn't, but yeah.
Hi. So just to address your question, because I've been teaching 801 for a long time, and it's solving the problem is not the only part of it. It's becoming an expert problem solver, understanding all the ideas behind the problem. So getting the answer is actually, this can be counterproductive, because then students haven't thought through the process. So what we have to do is, if they use chat to solve problems or something like that, then we have to also have additional practice about what is the meaning of what they did. What was the methodologies they used, thinking much more critically about the process. And that can be an important thing, which is often missed in many MIT classes. It's just get the piece set done, and that's it. So this is, bringing it to the next level, understanding what you did. So I think, there's this huge role for using the problems as an example for critical thinking, developing expert problem solving.
Thank you.
If you want to follow.
I just want to follow up on the great question, and what Peter answered. I think using the students in the classroom, interacting with the tool, with the chatbot, and being critical, trying to identify whether the tool is actually useful or not. This is helpful data for creating a critique model, a model that could be used for the second stage of these large language models, the training of them, which is the alignment training that essentially tries to nudge the large language model, assuming that this is a large repository of knowledge, to be helpful to other students. So I think interaction with students in the classroom would be helpful to train models that could be used for this reinforcement learning from human feedback, and the process could be iterated. And it's very interesting what the convergent point will be.
So I wanted to stay on the same topic. So I've never taught 801, but I've taught 802 many times. So in the same context as what Peter said, I didn't live through the arrival of the calculator, which was the example you mentioned, but I lived through the arrival of things like MATLAB and Mathematica. When I learned calculus in high school and at the very beginning of university, I had to memorize how to do tons of different integrals. That was a big part of learning single variable calculus. You don't have to do that anymore, which means that the way calculus is taught at MIT or at a good high school now, if you have a good teacher, it's much better than it was when I learned it, because you get to focus on understanding calculus and relating all kinds of real-world problems to how do you relate a real-world problem to the integral that you need to do or the differential equation that you need to solve. And so it elevates what you learn in an intro calculus class, or at least it should. And so to me, it seems like we have to, using the mechanics example in ChatGPT, we have to figure out what that elevation is. And in a sense, it's like prompt engineering. What everyone learned back then was the analog of prompt engineering, but how do you respond to a world in which anyone can do any integral automatically? And the teachers of calculus responded to that pretty well, at least at places like MIT. So
Yeah,
I think that's to me that's the meta example.
Yeah, here's an example. It's not quite prompt engineering, but something I had thought of in my interactions with ChatGPT. So right now it still makes a lot of mistakes. Like there's this problem of a cube sliding along and hitting a ridge and toppling, and what the minimum velocity was for it to topple over. And I could not get ChatGPT to get the problem right because it just wasn't applying the parallel axis theorem correctly. But I thought it might be interesting too to sort of, in the context of an exam, sort of a real world example now is more and more people will be using ChatGPT to solve things like this in real research, right? So you could imagine an example where you have students in an exam or for homework be given ChatGPT's response to solving a problem and find what's wrong, or figure out is it wrong or not. Follow its logic where it explains what it did. Kind of what you would do is someone grading an exam. And that develops a skill that is important in using ChatGPT, is learning to be critical of what it's spitting out and not just taking it at face value, because it sounds very confident.
What you just described is the way an expert problem solver thinks. And what we have to teach students to go from our input, which is students coming in from high school, and bring them to the point that they're expert problem solvers. And I don't think ChatGPT changes that.
Yeah, I agree.
Actually, this is an interesting opportunity for a segue, because one of the other questions that you posed on your slides is what happens when these models begin to dramatically outpace people. And maybe the way that experts actually think about problems is very different from how we right now think about problems as experts nominally. So I want to ask the general question, because I'm a pedestrian when it comes to the way these models actually work. I'm very curious to know from people in this room what the quickest path is and what the expected progression will be for us to get to that point. And I'll just spitball, give a little example of what might be one way we get there. So the question of context size came up earlier in one of the talks. And in that context, it was, hey, the context size is small. Humans are better at this right now. We're able to do things the models can't. That maybe the scaling is unfavorable to us. Maybe we end up with models in 5 years with enormous context sizes, and our working memories are actually extremely small. Most of my arguments are of the form, I know A and B, therefore C. Maybe I just can't think of some arguments that involve, a million terms at once, and that becomes feasible in 10 years. So I'm curious, as an open question, either a comment on that possibility or on any other route for us to get to models that are seriously, dramatically outpacing us. Any thoughts?
Sure. So I think if you want to make it analogous to humans, what you'd actually want to do is figure out a way to work with the finite context window, but somehow get it to integrate with databases so it's pulling in the right information it needs to act out like sequences, right? So if you think like what a graduate student does, they show up at MIT, they don't know so much about a subject, right? But over time, what they do is they bump into people, they get familiar with different previous works, right? They come up with quick, simple mental models for how to think about different aspects of that, and they write down a whole bunch of notes, which they come back and look at later, right? If you stood at the board and someone asked you a physics problem, maybe you could do some of them, but a lot of them you wouldn't be able to do the research kinds of ones. You need to go back and look at your notes all the time, right? And so I think to really push this forward to have an LLM be more like a human level AI, what you need to do is structure it in such a way that it can actually retrieve information and process that so it can actually act out like an autonomous research program.
One thing I would add is these things are already much better than us at certain things. This is maybe something Stephen Wolfram will say, that they're clearly much better at like deep computation already. They're good at doing some like machine learning algorithm that takes thousands of steps. We're not doing that in our head already, right? So what exactly are the axes you want to think about? Speed, maybe, working memory, the number of things you can kind of fit into your memory as a human is going to be probably way smaller already than these systems do. Deep computation, large databases, there's already kind of axes where it's, I think, drastically better.
I would just want to follow up on this discussion. I'm not sure if you've seen, recently there was a graph from researchers in Anthropic AI. Actually, they're building models with larger and larger context sizes for training. And if you trace out the final loss of the model after training, it goes down by increasing the context size. So it's an incredibly detailed plot, and you can imagine how much compute it has been to train it, because for every single context size they have trained it, but they see that if the model is seeing more during training, is becoming better in this next word prediction task, and supposedly that's very helpful for the abilities of the model. I think that's we will definitely see a very long context-sized models in the future. Currently, the models, I think GPT-4 has been trained with a context size of 32,000 tokens, which is about 50 pages. So it can see 50 pages in a single context and make inference about that. And I think we'll see much better models. One thing I want to go back to humans. I'm very of course, we may not be able to hold a very long context in our working memory, but I think something I'm really fascinated about humans is that we can communicate in a very efficient means through language, very efficient, with just a few bits of information, we can expand our context, and we can rely on the fact that other people are carrying a different type of context from us, and we can expand our understanding in this way. So another direction I think it's going to be very exciting is to see how these agents communicate with each other. And I personally think it's an open problem. What's the best way for large language models to communicate with each other, and how to utilize that communication? And I think we may be able to see advancements in that direction.
Yes, on that last thought, I think, isn't that one of the main concerns from, for example, Jeff Hinton, when large language models can communicate with each other, it's going to be unstoppable. And in the context of here, everyone trying to build models that are reliable and that are good for science, how does everybody think we should proceed in this direction? Like we heard from LeCun this morning that everything is all right, but there's a lot of people that are concerned. And I was actually wondering after his talk, this idea of not having to be worried about machines being much more intelligent than us because some students are more intelligent than us. I think I would like to hear everybody's thoughts on how we are fine-tuned evolutionarily to survive and for self-preservation, and that I think gives us empathy and to be able to be in a society and is beneficial for us. But computers do not have that evolutionary input. And so is there a way to make sure they have it? Or I would love to hear thoughts on that.
So I did actually just want to chime in on this discussion of some of the implications of it becoming this smart. So I mean, a lot of people have talked about the dangers of, like Max mentioned it, controlling like a nuclear arsenal, sort of the Skynet picture, right? One of sort of my concerns with its capabilities already and it becoming much, much smarter is the economic shock that could come with that. I think traditionally we've thought of automation as sort of replacing a lot of manual jobs. This is doing things that we train people at MIT to do, a large fraction, like coding. And I think that could add a lot of sort of unpredictability to the world. And like MIT should think about that seriously. That's one of the reasons I put the points of like, should we be thinking about adjusting some of our curriculum to make sure our students don't end up on a job market where their skills are not relevant anymore because one person with ChatGPT is now replacing 100 programmers in a company, for example. So that's sort of my 2 cents worth of where I've like been thinking about bigger concerns about the growth of this intelligence.
I mean, I would agree a lot on the economic front that, and especially as researchers, I do think that it's important to stay on top of these tools because I think we're going to start to see people who use these more and more start to outpace people who do not do that. And so I think leveraging these to speed up research and stay on top of what's happening is going to be very important. I think on the like AI safety front, I mean, I'm not an expert, but I would say that before you get too scared, while it is important to like think about this, I do think that you should specify what exactly you're talking about before you're too afraid of it, right? So if you want to think about these language models communicating with each other, right? They take a certain amount of time to communicate, right? They can only digest and output things at a certain speed. There's computational limitations to solving hard problems. And so the whole like super intelligence explosion thing is not necessarily something to be too worried about before you've talked about what exactly is exploding, right? If you just talk about AI in general, it's a black box and it by definition can almost do anything you're asking it to do, so that's scary. But if you talk about a concrete instantiation of it, then you can start to analyze it and like realize it has limitations as well, just like people do when they work with each other.
And I also think like in the coming decade with LLMs becoming more and more powerful, it's certainly possible that like a section of like people who like certain jobs will become obsolete. It is clear. So I guess the best policy is to, instead of stopping LLM research, we should think about how to retrain them or reskill them so that they'll have a job and then that sort of thing. So we should think ahead how it will impact and how we can reskill them so that they will be also useful. Like, we can leverage their abilities better. And another thing is like, so right now it's impossible for a person to load large language models in his laptop. Okay, because the size, the RAM requirements, the GPU, it's enormous. So it's becoming more and more concentrated. So we should also focus on how to make lightweight models so that people can try and so make it more democratic and then truly open source. And ideas in that direction will also help how to leverage, so yeah.
Yeah, actually, just to expand, I think that's an interesting point of like many of the models are very computationally intensive. We heard from some of the talks this morning on computer science that we just don't have the resources to compete with OpenAI and these big companies that have massive GPU clusters. But I mean, should universities think about pooling their investment like they do for facilities like the LHC so that they have their own dedicated research clusters that are kept separate from the corporate world? I don't know if what the answer there is, but maybe it's something to think about.
There are already these, Department of Energy sponsored supercomputer systems, which in principle are open across the research community. So perhaps the use cases for those will evolve towards these kinds of cases, rather than, let's say, up until now, the idea to use it for, brute force particle physics simulations or astrophysics calculations or whatever.
So, disclaimer, I'm the most non-technical person in the audience here today, but I'd like to speak to one of the items you had on your list, about how MIT can. First of all, should MIT do something to try and steer this whole disruptive technology, right? And I think MIT is very uniquely poised as an institution to help direct how this technology should and can be used. It's no doubt it's going to disrupt a lot of things. It's going to disrupt everything, all the structures that we know and that we have lived so far. So rather than be afraid to go with this, I think we should seriously think about how we can use it safely and sort of be the leaders in doing that. Thank you.
I wanted to address the first and the fourth bullet points here.
Okay.
Which, in a very simple way, I think, if you want to rethink what's going on in the classroom, instead of teachers being distributors of information, which the LLMs can do offline, and students can do that outside the classroom becomes a place where the teacher is more a coach of thinking in the classroom. And that model of thinking about dividing the distribution from the learning is an important way to change the nature of the classroom.
Yeah, I agree. Actually, in conversations over the past month about this, I think it may have been Mark that pointed out, perhaps the most similar disruption to the sort of rise of LLMs was the invention of the internet, when suddenly all of this information became readily accessible on Google that previously was much harder to access. Now it's even easier. Google, it still takes some work sometimes to find the solution to your problem or something to guide you through it. Now you've literally got Google talking back to you, basically, and explaining it step by step.